Welcome to the office. We want to take a look at another example that's very similar to the previous example that we looked at. In this example, however, what we're going to do is we are going to, right, very similar to the previous, I would like us to consider instead of modulo by what's generated by 1, 1, 1, here what's generated by 3, 3, 3. Now here's the tricky bit. Essentially, it works out to be about the same thing. If we look at that same figure, the same graphic here that we did in the previous example, if I were to change my line, so let's say I change the definition of my line here. Instead of t, 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 I want 3t, 3t, and 3t. So that's looking at this line right here. Oh, the line didn't change at all. And the 0.111 becomes the 0.333. Okay, I mean, that's that really different? Did I change anything? Yes and no. Here's the thing. I actually have the ability to move along this line a little bit because since I'm looking at what's generated by 333 now, this line does intersect with the XY plane right here. But what I can actually do is I can go ahead and move this line essentially up and down a little bit. I can consider what passes through here. And then what I can do is I can actually take a look at, right, so this is hitting this point and this point and this point. So I can shift everything down, right? So I don't actually hit 1, 1, 1. I don't actually hit 2, 2, 2. So I can move everything down by 1. And then I can move everything down by 1 more, and I get something a little bit different. So it's a little bit weird. Probably the easiest way to think of this is by returning back to our notes here a moment. And if I were to plot the point 0, 0, 0, so I'm going to embed this in two space here. So 0, 0, 0, and then up here I have the point 3, 3, 3, and my line passes through these. But the thing is as I move down here to -3, -3, -3, and up to say 6, 6, 6, I'm actually skipping over the things that are in between there. So when I look at the point here and the point here and here and here and here and here, for example, right, this is 5, 5, 5, and here I have 4, 4, 4, and so on, right? I can take this line. So before I could fill all of the 3 space with just these lines, but now I'm skipping over a bunch of points within each of those lines. So what I want to do is I want to fill in those gaps. So if I take this line and I shift it down by 1 to here, now I have all of these things. So now I'm getting this new line. It looks like it's in the same place, but I shifted it down by 1. And I can shift it down one more time. And when I shift it down one more time, then I get the remainder of what was covered by the 1 line now takes 3 lines to cover. So instead of it completely reducing to z, so here we have z cross direct product with z, direct product with z, and we are taking the quotient by, or modulo by, it's generated by 3, 3, 3. I still get all of the same lines, right? So I still have that this is isomorphic in part to z cross z. But the problem is that each one of those lines has 3 copies. So I can identify it by adding this z3 there. The coset groups, or the cosets of this can be identified by So earlier I said they can be identified exactly, right, in our previous example, they can be identified exactly by where they cross the xy plane, where the z value is 0. But the thing is here, there's not actually an intersection. So previously, where it intersected, the xy plane. This time, it doesn't actually intersect the xy plane for all of them. So what we get is essentially we still get A and B, for where is it on the xy plane idea, but the other bit of it is that we can have this sort of r sub 3 here, or just call it just leave it as r plus what's generated by 3 3 3, where a and b are integers, but r actually belongs to z3. And what would happen here is we would essentially, or we could create sort of a mapping that would bring us from, um, well, we could create a mapping that takes us from here to there, but that's not quite what I really want to do anyway. So, but the point is we can identify our cosets by these, and when we identify our cosets in this way, that very clearly makes it so that way we have that this thing is isomorphic to that. Okay, so identifying the cosets and using that coset identification to identify what our factor group is isomorphic to. That's what I'm trying to demonstrate here. So just a quick recap or a reminder. So far, we've looked at a few different ways of identifying how we're isomorphic, or what we're isomorphic to. So we have taken some results of theorems. Okay, cool. Hey, look, this theorem says that it's got to be this. Fine, that's fine. We also have the scenario where we look at the order of the factor group and say, oh, well, according to the order of the factor group, we only have these possibilities. And then maybe it's an immediate result, or maybe we have to look at the order of an element of that factor group to determine which of the possibilities it is. And then here we actually have the scenario of, again, looking at a geometric interpretation of the group and of the then the cosets of the normal subgroup. So we can use that description of the normal cosets to determine what we have for an isomorphic structure. In our next example, we're going to look at a different way, which is actually a little bit more fundamental and really quite convenient at times. And that example is where we just use a homomorphism and say, hey, look, this thing is, this homomorphism defines us a kernel. That's the thing that we want to quotient by, so wonderful. And then, hey, look, the result is isomorphic or isomorphic to what we're mapping into. So that's what we want to take a look at in our next example. So I'll see you guys back here in the office for one more example on these factor group computations.